great pleasure to have Matthew and Agius were speaking with us. So Matthew received his high education mostly at Malta, and he also worked at Southampton, and now he's working at the institution in Rome, but physically still he's in Malta. So today he's going to talk about the work that they have been working on like 4 or 5 years ago from the results from the OBS data in constraining the thickness of the mantle transition zone. And this topic has a broad interest for our researchers in the petrological chemistry community, but also in geodynamics community too. And we are very happy to see that. I'm very happy to see that we have audience here in this room that coming out from different disciplinary. So we're looking forward to your talk, Matthew. So there you go.
Thank you, Zhengzhu. It's an honor to give this seminar today. I also appreciate that to find a good time, especially because of the large time difference. So good evening, everyone. And as highlighted, I will be talking about a recent publication that the group that I'm part of has published. I would like to mention the co-authors. It's Katrin Reichert. She's the principal investigator of the experiment PILEP, which I'll be talking about. Nicholas Herman, also an investigator in the project. Saikirin Tarimana and Mike Kendall from the University of Oxford. The experiment is a large-scale experiment, as I will highlight. You can see on the map, we put instruments in the middle of the Atlantic Ocean to study the mid-Atlantic ridge. The area is a large area far away from land, and this costs a lot of money. The funding comes from the European Research Council and the Natural Environment Research Council in the UK. Now, as the experiment itself, the name PILEP stands for Passive Imaging of the Lithosphere-Asthenosphere Boundary. And as the name implies, the initial aim of the experiment was to study the lithosphere, how it forms beneath the Atlantic ridge, and how it evolves with time, and define the characteristics of the lithosphere at its very early stage. Now, lucky for us, the seismic data was of very good quality and gives us the opportunity to image deeper. And my work in this project was to focus on the mantle transition zone using the data from this experiment. Here we can see the seismic stations that are mainly available around the world. And for perhaps non-seismologists, this map shows how many instruments there are across the world. There are hundreds and thousands of seismic instruments, which gives us a very good opportunity to see and understand the processes that happen deep beneath the Earth's surface. The problem, as you can see, is that these stations are located on land, and leaving the oceans not sampled very well, as you can see. So the Pacific, the few stations that there are, these are on ocean islands in the Pacific, similarly in the Atlantic. So there's a problem in the resolution between areas which are beneath the land areas, because there are so many stations, and then areas beneath the ocean which are sparsely sampled because there's no stations. So this was another aim of the experiment, where we wanted to put high quality seismic instruments in the middle of the ocean, so we could study the processes that happen beneath the ridges. As you can see, it's close to the equator, and in this area there are some transform faults, one of which is the chain fracture zone and the other one is the Romanche fracture zone. Here's a closer map of this area. So the experiment, in total we deployed 39 ocean bottom seismometers crossing a width of more than 1,000 kilometers from east to west. So to go there, of course, we need sophisticated ships, we need special equipment. As you can see in this figure on top here, the instrument is, the seismometer is in this green bubble over there. And the instrument is very similar to the ones used on land, but it is enclosed in the sphere. It has to withstand the high pressures of the ocean. The ocean in this area is about 5,000 to 6,000 meters deep. So the pressure from the waters is enormous. So the instrument has to be sealed, watertight, and withstand these conditions. And then along with the instrument, you need digitizers, data loggers to store the data. And of course, you need batteries to operate the instrument and the data loggers. And all of this are stored in these tubes and in this blue area over here. The instrument, once it is left on top the sea, it will sink down to reach the ocean floor. Now, this takes about a couple of hours for the instrument to reach the ocean floor. The instrument sinks by about 1 meter per second, and it settles down at the ocean floor. We left the instruments there for 1 year. So we deployed the instruments in 2016, in March 2016. Then we went the following year in March 2017 to recover the stations. The stations are left totally on their own, and they are operated by batteries, and they do not communicate or send the data. So they are storing the data on board. On by themselves. And in a way, it was fascinating to come 1 year later. We communicate with the instruments using acoustics. And the instrument responds back saying, hello, I'm okay. And you give the instructions to lift, to go back to the surface. The way it's done is by the bottom of the instrument, this white square here, is biodegradable concrete. And it is attached, so it helps it sink. And then when it needs to lift back up, it disconnects from the rest of the instruments, and the upper part starts rising back to the surface. So it doesn't need any power. We just play with different densities. So initially it has some weight, and then it comes back without the weight. I would like to mention that the instruments are from Scripps in the US and from Lamont as well, and from IPGP in France, because we needed so many instruments, and instruments that can stay for so long at such deep sea. We needed the collaboration of these 3 institutions to provide us with the instruments. So for me on the ship, it was the first time, but the engineers who deployed these instruments, they do this in many places around the world. The experiment was very successful. So in total, we deployed 39 instruments and we recovered 37. So the data that we collected, you can see the green dots on the map. The green indicates that we retrieved some data or very good quality data. Unfortunately, the other 2 instruments that we did not pick up, one did not respond. So we don't know what went wrong with the instrument. And the other one responded, but it never came back to the surface. So it could have been that the instrument got stuck in the mud at the ocean floor. There would be a lot of mud, and the instrument might get sunk in the mud, which would have made it difficult for it to get back to the surface. But overall, the experiment was a very successful experiment. We got very rich data, and what I will be showing today are results from this data set. Okay, before I'll proceed, I would like to show this animation about the ridges and what we think that happens beneath the ridges. I am showing this animation because after we published the paper, there was a lot of questions from journalists saying that we already know what happens beneath the ridges. And what I would like to emphasize is that what we see in this animation is an artist's impression. And of course, as scientists, we need evidence. We need to get measurements. So I had to make it more clear for journalists that what they know is from ideas or from illustrations. It's just we need to do and get the direct evidence. Here's another example. This is from a textbook explaining plate tectonics, where we see that we have ridges and spreading, we have subduction zones, we have mountain building. So this is from a textbook explaining the process, but what is missing from this textbook is what is the depth that involves these processes. We can ask questions like, are ridges a result of slab-down wellings, like of things being pulled by gravity, and as a result we have an opening and this is the result of the ridge? Or is it that the ridge have active upwellings, which is pushing? So do we have pulling or pushing? The answer probably is a bit of both. Here's another example from textbooks, from science books, is that there we have a convective cell, we have hot material rising and then colder material sinking back. The figure is nice, but once again, we don't see a hint of the depth of the processes taking place beneath the oceans. Perhaps the main question is whether we have whole mantle convection or a two-layer system inside the Earth. In the case of a whole mantle convection, we have a heated core, we have hot material rising, we get hotspots at the surface, we get ridges where there's spreading. We also have subduction. The subduction can reach down to the bottom of the lower mantle and also sinking into the lower mantle, so from the upper mantle to the lower mantle. Or else, in a case of a two-layer convection system, we have these two layers which are isolated from each other. In the lower mantle, it is sluggish flow, things move very slowly, whereas we have a more active convective system in the upper mantle, which in this model, it can also explain subduction and ridges and hotspots. In the case of subduction, it seems that it doesn't penetrate down into the lower mantle. Of course, these are models, and over the years we have the opportunity to look into the data and see which best model describes the Earth. In the study today, I will be focusing on the mantle transition zone. So it is the transition between these two layers, between the upper mantle and the lower mantle. In the case of slab-down wellings, we have very nice pictures of subduction and slabs sinking down into the lower mantle. This is an example from Van der Hees from 1995. In this example, which is from seismic tomography, we see these colors. So the green and blue shade indicates faster shear velocities, which is representative of colder temperatures, lower temperatures. And in case of red shades indicates slower shear velocities, and usually it indicates higher temperatures. So in this case, we can see a subduction beneath Tonga, and we can see the earthquakes, and that it matches also with the seismic tomography, but perhaps it is going through the mantle transition zone. Now, this is from 1995. As years goes by, we have much more data, we have nicer images. This is for the Nazca plate and the South American plate. We can see that the slab is actually penetrating the mantle transition zone. And probably there's some remnant deep slabs which are stuck in the lower mantle. Then over the years, this is from 2013, we can see that the subduction slabs can have different structures and morphology, how they subduct. And these are for different places across the Pacific. So in some cases, the subducted slab is stagnated, it's stuck above the 660. In some cases, it's stuck underneath, it penetrates through. And anyway, we can see all these different structures of slabs, which clearly cross from the upper to the lower mantle. We can also look at global models from tomography. This is a map view. And because I will be talking about the transition zone, I'm going to zoom in on these depths. So for example, at 400 kilometers beneath Japan, beneath China, and around the Pacific, we can see these blue, faster velocities, which probably indicates the colder slabs which subduct on this area. And also on the other side of the Pacific, like South America and North America. also at 500 kilometers, and also at 600 kilometers. Now, the interest in my case is the mid-Atlantic ridge. And in this case, in this model, along the mid-Atlantic ridge, we can see relatively faster velocities. Now, I'm going to show another global model. This time it is from Ritsema group, where we have subduction, there's also the fast velocities, but in the case of the mid-Atlantic ridge, we have slower velocities. And what I would like to emphasize here is this issue about seismic stations. So where we have seismic stations on land, there are very good agreements between global models, but because we have very few stations or no stations at all in the oceans, and this leads to some disagreement between models, as we can see over here. So within the mantle transition zone, in this model, the one I just showed, we have these faster velocities, or relatively faster, whereas in this model, within the mantle transition zone, here we have slower velocities, indicative of higher temperature. So this highlights how important it is that we have this experiment and the opportunity that it gives us, that now we can get direct measurements from on top the mid-Atlantic ridge and also looking into the mantle transition zone. So what is the mantle transition zone? I believe that people watching probably are petrologists or geochemists, so they probably are familiar with this. The mantle transition zone basically is a phase transition in the minerals. In the case of at 410 kilometers, or approximately 410 kilometers, we get the phase transition from olivine to wazzelite. And in the case of the phase transition happening at about 660 kilometers, we have a phase transition from rigwitite to bridgemanite. And these phase transitions are also detected in the seismic waves which travel within this depth range, as I will show you in these examples. There are different ways how we can see this discontinuity at 410 and 660. For example, one example is from a technique known SS precursors, seismic SS precursors, where we have an earthquake on one side and we have stations on the other side. And the seismic waves travel and it bounces off from one place to the other, reaching the station. The advantage of this technique is that it can sample places where you don't have instruments. And here is an example from global models. So in this global model, we are seeing the discontinuity at 410 kilometers, how it changes in depth. So in some places, this phase transition happens deeper, and in some places, it happens shallower. In the case of the Pacific, for example, we can see that it happens, in some places, it happens deeper. In the case of the Atlantic, it might happen deeper. It's not so clear what happens beneath the Atlantic. Here we're seeing the example of the phase transition happening at about 660 kilometers. And we can see that beneath the Pacific, in some places, it happens shallower. In the case of the Atlantic, some places are shallower, and some places it might be deeper. We usually look at the difference between the two. So the difference between the depth of the phase transition at 660 minus the depth of the phase transition at about 410 kilometers. And the difference here, we can see that beneath the Pacific Ocean, it is thinner, whereas it's not clear what happens in the Atlantic. Now, keep in mind that these images are very low resolution in the sense that when you have an earthquake and it is bouncing from one place to the other, you cannot just assume that the place where it is bouncing, it's a small point. It is actually a very large area. And here, these are what we call sensitivity kernels, Frechet kernels, and it shows that it could be even more than 1,000 kilometers. So this point here is a very large area of about 1,000 kilometers. So the resolution that we have here about the transition zone thickness and the discontinuities is very large scale, low resolution. Let's see some examples of higher resolution. Here is an example of the changes that happens in the 410 and the 660 beneath the Japan Islands, reaching all the way to China. The blue shade, the blue and the red, is from seismic tomography, blue indicating faster velocities, indicating higher temperature. And in the case of the red, it's slower velocities and higher temperature. So this is cold and this is hot. This is from seismic tomography, and this is from seismic receiver function. The power or the advantage of using seismic receiver function is that it can detect any changes that there is in density, such as at 410 or 660. As you can see, the 410 here, you can see this very smooth line where the phase happens, whereas in seismic tomography, you cannot see it. In the case of the 660, you can see that in this example, there is some topography, some variation in the 660. And the reason is that there is this cold subducting slab resting on top of the 660. And because it is colder, we are having that the phase transition is appearing in some places to be deeper. Okay. So the 410 and 660 are influenced by temperature and pressure. The cold slab is of course colder and it is sinking, so it is going into higher pressure, and it will affect at what depth the phase transition happens. Here's an example of an area where we expect hotter temperatures. This is Hawaii. And here we see this cross-section from northwest to southeast. A similar experiment of ocean bottom seismometers was deployed across Hawaii. There was about 70 stations in the ocean. And here is a cross-section from this analysis that was done with receiver functions, showing that the 410, in some parts it rises, in some parts it goes deeper, rising and goes back to its expected depth. The 660 is relatively flat. If we have to look at this on a map, we can see that at 410, the discontinuity changes depending where you are. So in white are the islands of Hawaii. In the central part, beneath Hawaii, we have a deepened 410. So the 410, the transformation happens at a deeper depth. Whereas surrounding it, the 410, the phase transition happens at a shallower depth. This is very interesting, and it matches geodynamic models. So in this model, we can see that there is a plume stem beneath Hawaii, and it predicts that there is a cold curtain sinking back into the mantle. And this curtain around here is what we see around the islands of Hawaii. So this is a very nice example where there are geodynamic models and then matching with the data that we have for Hawaii. If we look at the transition at 660, we can see it's relatively flat. So we were seeing the cross-section from northwest to southeast, which is the line over here. But the 660 tends to be shallower towards the south. If we look at the depth difference, so the transition zone thickness between the two, we can see that it is dominated by the 410, which surrounds the island. Okay, so what do we learn from this? So what we expect from the mantle transition zone. When you have lower temperatures, that means colder, the 410 is shallower, and the 660 or the transition here, we end up with a thicker mantle transition zone. And in the case, if we have hotter temperatures, we expect a thinner transition zone. We usually use the mantle transition zone thickness as a robust measurement because any anomalies above 410 kilometers are cancelled out when we cancel the 660 minus the 410. So we usually look at the thickness of the mantle transition zone. So far, we've seen examples of subduction. We've seen examples of Hawaii where we have a mantle plume, but it's not yet clear what's happening beneath the ridge, and this is the focus of this study. So we used earthquakes of about magnitude 5.5 from around the world recorded on the PyLab network. This is just an illustration where earthquakes come in from all around the world. And here's an example of a receiver function and how it looks like for those who are not so familiar with seismology. So here we have an ocean bottom seismometer. Here we have an earthquake, and it generates a P wave. The P wave is recorded on the ocean bottom seismometer, And as it goes through the different layers inside the Earth, it will experience a seismic phase conversion, which we call a P2S conversion. And we get one for the 410, which I'm showing in red, and one for the 660. We call these P410S and P660S. So this is how a receiver function looks like. Basically, we use the vertical and the radial component recorded on the ocean bottom seismometer. And this is the arrival of the phases of the P2S at 410 and the P2S at 660. One's at about 42 seconds from the P arrival, and the other one is at about 70 seconds from the P arrival. The time difference between the two gives us an indication of the depth of the mantle transition zone. So if the time between P660 and P410S is less or gets closer to each other, the delay time is less, then it suggests a thinner mantle transition zone. If the time between the two increases, then it suggests a thicker transition zone. And here is a result from this. So basically the triangles are the instruments that were used in the studies. The crosses and the circles are what we call the piercing points. It's where these points cross at 410 and 660. And the blue circles here are the earthquakes that we used in the data analysis, which you can see they are from different parts, opposite directions of the network. The circles, the colored circles, represent the time difference between the two. So the P660S and P410S, which is the time of these two peaks over here. And as you can see, towards the west, the time difference becomes less and less. I really like this example because here we are looking at the raw data, so no inversion, no migration of the data, but we're actually looking at the raw measurements. And what it tells us is that towards the west part of the ridge, the thinner zone, the mantle transition zone is thinner. We can then use this data to migrate to a 1D model, and we can also migrate to a 3D model. So here, I'm going to use the data within each of the circle and migrate them into a 1D model. And basically now, instead of time, we have depth. And you can see that the peaks of the depth correspond to at about 410 kilometers. In the case at the bottom one, it corresponds to the 660 kilometers. The background color are the shear velocity, which is from the mantle global model. So what we see here is the 660 is clearly rising on the western part, and the 410 slightly dipping on this side. And what's nice about this picture is that it coincides with the low shear velocity. So if we have higher temperature, we expect the low shear velocity to be, lower, and we expect a thinner mantle transition zone, like what we see over here in this example. We use the data also to migrate to a 3D model. So essentially we take each waveform in all the directions that it's coming and recorded on the different stations and migrated in a 3D space, which gives us an opportunity to see how the mantle transition zone is across a space, across an area. Here we can clearly see that the 410 is going deeper over here and the 660 is rising. And these are coincide in the same place where we have the deepen and the elevated 660, resulting in a thinner transition zone. Here is a view from on top from a map. We can see the 410 going deeper in this part. In case of the 660, we can see that it is being elevated all over here. And what's in a way nice to see is that it goes back to its expected depth further away to the west and further to the east. If we look at the difference between the 660 and the 410, we get the mantle transition zone thickness. And this is the main result where to the east we have normal mantle transition zone thickness, which is about 250 kilometers. But then to the west, we get a thinner mantle transition zone, which is a strong indication that it is a result of higher temperature. We looked also at other studies in the region. This is from precursors, the SS and the PP precursors, the ones that I mentioned, where there's this bouncing that happens at the surface of the interfaces. And what is nice to see is that the experiment pileup was taking place down here, but other places, the phase transition of 660 was actually happening also elevated. So here you have these depths of 630 instead of 660, and you can see them at the outer edge of the African plate. In the case of the 410, it's either at 410 or slightly deeper, also in the far edge of the African plate. Now, earlier, Zhengzhu asked me if there were any challenges with the reviewers. The key question we got from the reviewers was whether what we see in the pileup experiment is just a local observation. Maybe we were just lucky to be in this place to see this observation, or whether it was a large scale all along the ridge, or perhaps even a global feature. So to answer this question, we looked at global models. And this is an example of three different global models using different data sets and also at different times. So the waveforms, they would have different data sets, and all three of them, as you can see in this example, that beneath the ridge, there is relatively slower shear velocities. So basically we took the average shear velocity within the mantle transition zone between 400 and 660 kilometer depth. We took the average and we plotted it on a map. This is also an important observation in the sense that usually in the case of global models, many people trust what the models see, where there is subduction zones, and mainly back to the issue that because there are seismic stations on top on land. And people tend to trust less the models beneath oceans because less data and less resolution. And what this is showing is that these stream-dependent models show similar patterns. So even though there are few data in the ocean, all three show a similar pattern. The reviewers asked us to look into more models, not just into these three models. And so we looked at more models. We also took a statistical approach, where basically we took bins along the ridge. What you see, the color here is the distance away from the ridge. So we took these points as distances away from the ridge. The black dots are volcanic islands or hotspots. So we ignored data from these hotspots. So we avoid any influence from hotspots. And then we generated these histograms. So what you see here is the velocity on the y-axis and the distance away from the ridge on the x-axis, corresponding to the colors that you see on this map here. And here we have a clear pattern that closer to the ridge, we have slower shear velocities, and then the velocity increases as you get further away from the ridge. These are the two other models that we've seen before, where there is this pattern, a similar pattern for all three models. As I said, we looked at more models as requested. These are different models that are publicly available, like SizeGlobe or SUMM. These are two recent models for South America and North America, and all models have this pattern that beneath the ridge, even if it is slightly faster than zero, you can see the pattern that beneath the ridge, the velocities are slower compared to data from distant areas. And the only perhaps model which doesn't show this pattern is this one over here, the Studi. The reasons could be various. For example, different data sets, different parameterization. So it remains uncertain why this model shows a different pattern. We also looked at temperature estimates. So we can determine the temperature estimate depending on how deep or elevated is the 410 or the 660 or the thickness of the mantle transition zone. These are called Clapeyron slopes, which are empirical relationships based from laboratory tests. And what you see here, the black diamond is from the PyLab experiment, which for the 410, it suggests about a higher temperature, about 60 degree Kelvin higher. And these are from other places. So for example, Iceland, which is about 200, and other places. So what we find is that in the case of the mid-Atlantic ridge, it is hotter, but not as hot as hotspots or other volcanic places. In the case of the 660, it is a similar situation. Now we can, in the case of PyLab, it's about 140 degree hotter, but it is still relatively less hot than other places that we find like in the Africa or India places. If we look at the transition zone thickness, so we use the thickness of the transition zone to have an estimate for the temperature. Again, we can see that in the case of PyLab, it is less than places, let's say, than Iceland or West Ethiopia or Hawaii. And in a way, it is an average of what we see from 660, which is about 140, and 410, which is about 60, so somewhere in between. Interestingly, the temperature estimate seems to suggest that at 660, it is hotter, and then it cools down, being less hot towards the 410. Other data sets that usually people would consider, people usually compare mid-ocean ridge basalts with ocean island basalts and argue that there is a different chemical signature. We came across some papers. There's an example from Levoyer from 2015, and they collected samples along the ridge. And they do report that in some locations, they are characterized by mildly enriched isotropic signatures, which they might not necessarily be directly linked to a plume, but they do add additional support to a lower mantle original beneath the mid-Atlantic ridge. So if there are geochemists in following, this could be an interesting part of the research to look again into basalts originating from ridges. And then there are also geodynamic models where they describe these bismuthite enriched ancient mantle plume structures where you have these convective cells, where basically they could suggest that lower material could be different and could have different isotropically enriched, but relatively weak and depleted material surrounding sluggish, slow-moving bismuthite lower metal. And this could end up in some places, sometimes in preferential supply like hotspots or other places. So this could also be interesting to explain our results. So in conclusion, we find a thin mantle transition zone beneath the equatorial, the area where the PyLab experiment, but looking at global models from shear velocity models, it seems that this is a large-scale feature, at least crossing the Atlantic ridge. It remains unclear whether this is also observed, a thin mantle transition zone is observed or is found beneath other places like the Pacific, for example. And lower mantle upwellings beneath ridges may actually help to drive the spreading beneath ridges. I guess that's my final slide. And thank you for your attention.
Okay, thank you very much, Matthew. Now it's time for questions. I think we do have 20 minutes for interaction with the audience. And I do think that people have various questions. So feel free to raise your hand, or you could also type a question and I could read it on your behalf. Okay, Wenjun, yeah, you could open your mic to ask a question.
Yeah, thank you. It's a great talk. Could you please show you the last slide, please? Thank you.
This one?
The last, the second last.
Okay.
The final conclusion slide, yeah.
This one or this one? Sorry.
Yeah, this one.
Okay.
It's really great work. I have read your paper. Yeah, it's very impressive. But not that one. Previous slide. So, yeah, the conclusion slide.
Yeah. I think this is
Yeah.
right.
So,
The conclusion, because there are several seconds delay.
Oh, yes.
okay. So my question is that is it really mid-ocean ridge related transition zone? I mean, the left part, the tomographic model does not show the left part. So if we can see, I don't know what is the left part, but it's more like a plume, right? From deep mantle, from the low mantle. I mean, it may not be a simple mid-ocean ridge, but actually it's more like a plume-related thinning transition zone, right? I'm right? I don't know.
Okay, so the motivation to have the pilot experiment in this location is because it is away from known plumes. And in the figure that you see here, the dots that you see are volcanic places or that might originate from plumes. And the bigger the circle, the black circle, is the classification of the type of plume. So, for example, Iceland is a big black circle because we know it's a well-known plume. But then there are studies which classify the volcanoes and like Agius and other places like Cape Verde in how the origin of these volcanoes. And basically, you can see that the closest volcanic activity is the Agius Island, and it is classified as a small or relatively low rating in case of the plume. It remains always a debate whether it's a plume or not, but I do hope that the shear velocity models convince us that actually this is a feature of the ridge. As you can see in this global model here, or like I've shown before, that the feature low shear velocities, you can see that it follows the pattern of the ridge. Of course, beneath Iceland, you have slower shear velocities, but the pattern is very clear. Also, from these tests, we took the data avoiding the plumes. So the bins that we used are the colored ones. And where we have the volcanoes, we kept a distance away to calculate these histograms. So I think statistically, it is statistically significant that beneath ridges, there are low shear velocities. I do appreciate that from global models, the debate will always remain that there is no stations or the coverage is very poor. This debate remains there, but maybe it's about time that with this new observation, we should take into consideration that what they see beneath the oceans we can rely on it. So this was the motivation behind this test. And the pattern is clear. We avoided the volcanoes, so we took the shear velocities in normal mantle transition zone conditions. I hope this answers your questions or in a way convinces you.
Yeah. Okay, thank you.
Okay, another question. I think you answered the second question that people typed.
Oh, there's the
text. And here in the third one, that is the observation of the seismic velocity from the OBS verified by geochemistry work, and how large is the chemical anomaly that caused this seismic velocity anomaly.
I'm rereading the question. So observational velocity verified by the geochemistry work. Okay. How large is the chemical anomaly to cause such a velocity anomaly? So no, we haven't yet looked into the geochemistry involved. Usually when people look at the geochemistry, they look at the amplitude of the receiver function. So typically they would look at the amplitude of this, and sometimes they also look at the amplitude on top of it. So it is interesting, for example, that the amplitude above the 410 here is negative, and it's quite strong. Sometimes this is associated with some melt happening on top of the 410. But I did not look into this, and it would be interesting if maybe a geochemist looks into this. So to answer the question is no, we did not look into the geochemistry, and I don't know how large the required anomaly for this.
Okay, another question from Chen Yingfeng. So what's the pattern of the mantle transition zone thickness? Thinner to the west and thicker to the east is quite asymmetric relative to the ridge. So what is your opinion on that? What is your thoughts? Why this asymmetric distribution?
I was reading the question. So, okay, the asymmetric distribution. So we're talking about this figure. So for me, personally, it's not so obvious whether there is asymmetry or not. The reason being that in actual fact, the thin mantle transition zone is in the center, or kind of in the center of the Romanche fracture zone. And then the ridge continues further to the west, and in this case, it is further to the east. So if one assumes that the ridge is over here, then yes, it is slightly offset. But if you look on a map, it's interesting to see that it's actually in the middle of the Romanche fracture zone. Also interesting to note that the Romanche fracture zone is the largest fracture zone along the mid-Atlantic ridge. So this could also be interesting why the Romanche fracture zone is so wide. If maybe people were confused to see this figure, thinking it is offset, which kind of is, that line is over here. Okay, so the vertical answer I can give is when we look at the global models. So if we look at the pileup experiment on its own, we will always remain in the debate whether are we too close to a hotspot or not. So this is why I prefer to answer this question using this global model, these examples from global models. The black dots that you see are from hotspots in the area. And the mantle transition zone, the shear velocities, the average shear velocities, as you can see, are much slower beneath the ridges. The anomaly is not so big. It ranges from between 0 and minus 1%, but the pattern is there. And this is why we did these tests, excluding data from these hotspots and volcanoes to get into the statistics. So my reply, whether there's any influence from hotspots, is that if we exclude the areas where we know of hotspots, it is statistically significant that beneath the ridges, the mantle transition zone has slower shear velocities, as can be seen from these different models. So the pattern is clear that beneath the ridge, they have slow velocities, and then increases as you go further away from the ridge. Otherwise, yes, the debate will always remain there. Is this, are we too close to a hotspot? So this is why we looked at other data sets to get a better picture.
Okay, another question is that, is there a possibility of linking the thickness of the mantle transition zone with the water content in the mantle transition zone? Okay.
So water plays a role in the depth of the 410 or of the 660, and typically water is expected to be found in places where there is subduction. So as the slab is subducting, you have the dehydration, and this would affect the mantle transition zone. In the case of the ridge, we do not observe the patterns expected when you see water. Back to the question of water, here's an example showing that if you have subduction, you get the hydration, and you have wet, and beneath ridges, it's usually expected to be dry. This is the effect, the dashed line is the effect of water on the phase transition. And with the technique I just showed, we cannot differentiate between the two. Nonetheless, the results remain the same because we see a thin transition zone beneath the ridge. Now, sorry, the next question. Chat.
Yeah, the relationship, the linkage between the mantle transition zone thickness and the spreading rate of the mid-ocean ridges.
Yeah, we didn't look into this. It's for us. It's also not clear. I don't see it like there would be a direct relationship. One has to take into consideration that the 410, the 660 might be hotter than the 410, as we see, and this might also have an effect on the vertical movement of the rocks. So we haven't looked at the direct relationship of the spreading and the vertical movement, although probably it would be on the order of a few centimeters, millimeters a year.
Okay, I think another previous question that we missed is so how about for example, the effects of other minerals that are not olivine, meaning garnet. So what about the meteorite to bridge-mantle transition, for example, have the impacts on the thickness of the mantle transition zone?
I think there was an example of a garnet transformation beneath Iceland, where because of the very high temperatures or the inferred high temperatures, instead of the 660 being elevated, it actually deepens. And this, if it happens, is likely because of the garnet phase transition. In our results, we don't see this. We clearly see a thinner transition zone. The anomalies that we see, especially if you infer them to temperature, are lower, much lower than what is seen in Iceland. So also there was an earlier question about the temperature. The temperature is not a very strong anomaly. It is there, but it is much less than other places, including Iceland. I think I have this figure in there. So the black diamond, which is from PyLab, the experiment, is much less than what is seen in other places. In the case of Iceland, for the 660, the temperature is probably very high, which then would lead to the garnet phase transition, which we don't see then.
Okay, so it's 1 hour. It's perfect. So thank you very much, Matthew, for the talk, and also it's a lot of interaction with the participants. So, okay, thank you again, Matthew.
Thank you for the invitation. Once again, I truly appreciate that. I think over there it's 10 p.m. now. So good evening, good night, everyone. And thank you for joining in.
Yeah, thank you, and have a good day to you, Matthew. Bye-bye.
Cheers. Bye.